Hello, my name is Lucas Esper and this is Lab 3 Macroscopic View of DC and RC Circuits for Physics 2212 at Georgia Tech. This is the table of contents. I'll first begin with a brief introduction to the lab, then I will discuss series circuits, RC circuits, and capacitors. I will finish by answering some key questions. The summary of my results is on the slide. The purpose of this lab is to use principles of energy conservation and current conservation as it applies to circuits. We will predict the behavior of circuits containing resistors both in series and in parallel. We will use voltmeters and ammeters to measure potential difference in current. Finally, we will examine the behavior of capacitors. The fundamental principles that are needed for this lab is current conservation, also known as the node rule, energy conservation, known as the loop rule, and Ohm's law, which relates voltage, current, and resistance. The first scenario is a series circuit consisting of two resistors, two ammeters, and a battery. We were asked to calculate the current I1 and I2. The calculated current was 0.02 amps. This current is the same in both I1 and I2 because the resistors and battery are in series, so the total resistance is just the sum of the resistance from each resistor. The next thing to do was to connect the ammeter backwards. When the ammeter was connected backwards, the current had the same reading. When the ammeter was replaced with a voltmeter, the current was 0 amps because the circuit was open, and the potential difference was 3 volts. When the circuit is closed, I measured the potential difference across different parts of the circuit, and these were the results. Notice that the sum of all the potential differences equals 0, in accordance with the loop rule, which states that energy cannot be created nor destroyed. Here is a graph that shows the potential at different points in the loop. The battery raises the potential, the wires do not change the potential, and the resistors decrease the total potential. This is a visual representation of the loop rule, because the total potential at the end of the loop is 0. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? The voltmeter has a high resistance and essentially no current flows through it, making the ammeter reading stay the same. Now replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. What happens to the current through the other ammeter? Why? Both of the currents read by the ammeters change to 0.06 amps because the current is split at the node between the two paths. This is because of the node rule, also known as conservation of current. I was asked to calculate the resistance of different circuit elements. I used Ohm's law, which states that resistance is equal to the absolute value of the potential difference across the component divided by the current. The results are as shown. The calculated value for resistance in the resistors is consistent with the lab document. Next, I moved on to the portion of the lab dealing with RC circuits. When a light bulb is connected in series with a battery and capacitor, the light will start out bright and slowly dim until it goes out. This happens as the capacitor is being charged. When the battery is disconnected and the charged capacitor is connected directly to the light bulb, the light will start out bright and slowly dim until the light is out. This happens as the capacitor is discharged. I recorded the times for the capacitor to charge and discharge when using a bulb of 10 ohms versus that of 20 ohms. It takes approximately twice as long for the capacitor attached to the 20 ohm bulb to charge and discharge than for the 10 ohm bulb. Next, I moved on to the third part of the lab, which deals with analyzing time-dependent voltage changes across a discharging capacitor. We are dealing with a 30 ohm bulb and a 0.2 farad capacitor. Here is the data I collected. I collected data for 20 seconds and took note of the potential difference across the capacitor as it was discharging. The equation for delta V shown is the potential difference for a discharging capacitor. The potential difference decreases exponentially until it reaches 0. This equation was then linearized by taking the natural log. This is the graph of my linearized data. Next, I analyzed the graph that I created. According to the linearized equation, RC is equal to -1 over the slope of the graph. The slope from my graph was negative 0.1668, making RC equal to 5.995. I then compared this result to the theoretical result, which was found by multiplying the resistance of the bulb and the capacitance of the capacitor. The theoretical value was 6, which was consistent with the experimental result. Now I will answer some what-if questions. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? In real life, the reported current would be lower since real ammeters are not perfect and have some amount of resistance. In the lab, we assume the ammeter has 0 resistance. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Our ideal model predicts the capacitor would be charged instantly. This is because the model assumes there is no resistance in the wires. In real life, it would take a longer than predicted time to charge the capacitor because wires still have some degree of resistance. Thank you so much for listening.